Okay, so let's see what other questions we have regarding, our lecture on serial communication. So following up with this baseline wander question, the first question was, why do we have baseline wander and why does it occur? And the second is, why don't we actually use a DAC? Yeah, so we don't have a dedicated DAC because, there are many different protocols that are there, and a DAC could be part of the system, for discrimination, but this was just a way of having the baseline and it's as part of the signal, right? Because on average it has a pretty good baseline, but if you have too many zeros or too many ones, then that screws up this baseline. So similarly, I would ask the same question, why don't we just have another clock line? If you have another clock line, then I don't have this problem, right? So of clock recovery, because I know exactly, when the transmitter has, a clock boundary, and I can do that, right? But that's asking for more resources. That's saying, okay, well, I need another dedicated line. Here it's saying I need another DAC, because when you set up your communication, you set what the high is, what the low is. It does not always have to be 5 volts. And so that is all configurable. And then to have a configurable DAC to be able to do that is going to introduce a lot of complexity. So the initial idea of these serial communication protocols were, how can we have minimal number of wires and minimal circuitry and have an extremely ultra low cost, but pretty reliable communications channel. And so because hardware was really the bottleneck at that time, right? So then that forced a lot of the innovation to come from the coding side. And by coding, I just mean that, well, we need to introduce some more entropy in these signals so that we can actually get enough transitions in the signals to prevent or to reduce the problems of baseline wander and clock recovery over there. So it's basically saying, let's, hardware was too expensive and it's getting too complex to put this for, programmable sort of communication channel, because then for each kind of communication protocol, we would have to have like a different DAC mechanism. So then they started to work with different encoding and said, okay, well, maybe we should have, it's cheaper for us to speed up the clock at that point in time and send data at a faster rate and actually encode the data now, say using Manchester encoding, where every 1 is a rise from low to high and every 0 is from high to low. And that forces every bit to actually introduce a level transition over here. And that has enough, that basically provides like maximum entropy in the signal over here. So, and then there are, many other ways of encoding, right? So you have 4B, 5B encoding. There's also 8B, 10B encoding, which is kind of the same thing, but it's just saying that for every, 4 bits that you have that do not have good transitions, we're going to map that to a set of 5 bits that have a lot more transitions. So you can always see that in the 5-bit column, there are a lot more transitions than, in the 4-bit column here, assuming that, you're just following like a transition on the ones over here, right? So, okay, any other questions? You can speak up also, it's fine. Okay, so let's go to channel capacity. We did that a little bit quickly last time. So channel capacity, starts from the basic question about channel capacity is saying that, okay, you gave me a wire and, I should be able to pump, 10 bits per second in that. I should be able to pump 100 bits, 10,000 bits, 10 million bits, 10 gigabits. Is there a limit to sending, over, a channel? A channel could be a wireless channel, underwater channel. It could have any kind of medium, right? It could have an electromagnetic medium. It could have longitudinal waves as a sound channel. It could have also just communication over twisted pair, copper wire, or optical fiber, right? So the question was, well, as you, what happens if I send, a message across um, at a very fast rate, right? Say the receiver can receive at whatever rate you give it. So you can receive and I can send at a very fast rate. But why is it that, we can't send, uh, why can't I send you more bits, over say this channel, right? Or if we have 10,000 people on this Zoom call and everybody sharing their videos, why is it that we can't manage that? Okay, assuming that the receiver can receive as much as the sender is sending. So why do you guys think that could be a problem? So look at this figure right over here. I have this clock now, and this clock is basically running at twice the speed as the data, right? So let's say now I increase this clock, or I increase this data now to run at a faster rate, and then the clock is running at a faster rate. And so what's going to happen when I start increasing the data? So who can tell me what's going to happen here? So just say I have the same clock, like let's say, forget about the clock signal right now, right? I just have, this is a clock tick over here right now, but I'm going to send 10 times more data. What's going to happen to this? Like what am I going to see over here? Just in this first block here. Now I'm going to send, instead of just 1 bit, I'm going to send 10 bits over here. Yeah, I don't assume someone else will answer. I can just chill out. I mean, you answer it, right? It's perfectly good interview question, right? Why can't I, if I send 10 bits, 100 bits, 10 million bits more, what's happening here?
So will it be always 1?
Let's say I send 10 bits in that time, right? It doesn't matter if it's ones or zeros. You're actually going to see 10 bits over here, right? In the same amount of time, I'm actually going to be sending 10 different things here. And let's say that they all transition, right? So let's say we're not talking about baseline wander or synchronization as much, but we're basically sending 10 bits in that same amount of time over here, right? And so let's say that this time over here was 1 microsecond, and I'm sending 1 bit every microsecond. So what is that? What is that rate? 1 bit every microsecond. How many bits per second is that?
Is it 1 gigabit per second?
1 gigabit or 1 megabit?
Megabit?
You tell me. So just 1 bit per microsecond. How many microseconds in a second?
10 to the 6.
Yeah. And how much is that? So how many bits per second?
1 million.
A million. So 1 megabit per second. So I'm going to be sending now, instead of 1, I'm going to be sending, if I want to say now, I want to send, like 1 gigabit over here, right? So I'm going to be in that space of 1 microsecond. Now I'm going to send 1,000 bits, right? So why can't I send 1,000 bits? I mean, or why? What's going to make? What's going to change?
I mean, like, if the data waveform is too high frequency, then the last 2 sentences on the slide just won't be true anymore. Is that what we're trying to get at?
No, what we are trying to get at is, so you're right. I'm just looking at some really common sense observation, right? So yeah, so now we're going to see the data frequency is going to be really high speed. now, and we are sending 1,000 bits in the place of what we were sending 1 bit for. So what's going to happen now is that, first of all, you're going to have the rise time, falling time, rise time, falling time. And if we aren't able to make the signal rise as fast, then it may not rise all the way to 1, right? So let's say if we can push it all the way to 1, then we have a clear signal. But if the signal doesn't reach all the way to 1, it reaches 80%, but then gets pulled down so fast, and before it reaches 0, it gets pulled down. And so now the signal, in terms of the magnitude, it is not reaching a clear 1 and a clear 0. And it is actually just oscillating somewhere in the middle, because it's not able to pull up and pull down fully. The second thing is that on the receive side, right? So this is where the whole channel capacity problem starts to happen. Is on the receive side, it's trying to figure out when did this bit end and when is the next bit starting. And on the channel itself, it's not going to get like the same, it's not like if I sent 1 bit and then the next bit, they go at the same speed. Actually, they go at different speeds also, right? So they're bouncing across the channel. So even within a fiber optic wave, you have a direct communication through, say, the middle of the fiber optic line, but then it's also bouncing along, the boundary of the fiber optic cable itself. And so the signals that are bouncing across the boundary of the fiber optic cable, like within that, and they're going across, they take a little bit longer time to reach the receiver than the signal that went directly. So you actually have multiple paths. So you're sending one signal through, but they basically get split up. So let's say, you have your laptop and it's connected to Wi-Fi, and there is an access point, say the access point is right behind me, right? So the access point is broadcasting that energy from its antennas, and the energy is coming, in many different directions now. So there's 1 unit of energy that is coming out, but that 1 unit of energy is basically going over a sphere, and that energy is basically coming directly to the antenna on the screen of my laptop, but the energy is also going across the room, bouncing off the walls, and then also coming here. So at the end of the day, I'm getting, multiple versions of the same signal that I'm receiving at this end, right? So now what is happening so there are 2 issues, right? So one issue is to do with noise itself, right? So when I'm sending a signal at a higher rate, I have to deal with noise, because on the receive side, the signal will have to still go, say if I'm going from 0 to 5, on the magnitude side, if I'm, say, able to go from 0 to 5 volts and back and forth, I may not be able to go all the way to 5 volts and all the way back to 0. I'm actually, my signal strength is actually decreasing. Or let's say if I send a wireless signal now from the access point to my laptop, the air interface is actually absorbing a lot of that electromagnetic energy, right? What is Wi-Fi? Wi-Fi is running at, say, 2.4 gigahertz. And guess what your frequency of microwave also runs at? It's very close to 2.4 gigahertz. And because that's the frequency at which, water absorption of electromagnetic radiation is maximum. And and so essentially when you have more humidity, then more of your Wi-Fi signal is actually getting absorbed by the air. And indoors, the Wi-Fi signal is bouncing off the walls, and you're getting many sort of replicas of the same signal at the receiver. So net at the receiver, you're not getting exactly the same energy that went from the transmitter to the receiver, because the medium itself is absorbing that energy. So now the medium is absorbing that energy, and therefore that you're not getting a full signal. And the medium itself is introducing sort of aliases or echoes of that signal, and you're not able to then clearly discriminate, hey, is this signal, because I'm not getting the full energy of the signal, it is getting absorbed by the medium. And also I have sort of aliases of my signal, because the medium is causing that. So what we see with when we want to receive a signal is that we need to, in order to discriminate, is this a 1 or a 0, I need to know at least this amount of the signal, the signal strength is above a certain threshold to be able to discriminate that. So what Shannon's theorem in terms of, the capacity theorem came about with was to say, well, for a given signal, and if I have like, the capacity of the signal over here with the channel bandwidth, right? So channel bandwidth would be like how many hertz do I, or how many megahertz do I have? So like say Verizon is given, 1 megahertz or 100 kilohertz at 1900 megahertz band, and say, okay, well, this is your bandwidth, right? So now Verizon is given, let's say 1 megahertz of that's of prime, cellular channel space, and they basically have to pay like $20 billion for that to be able to lease that for 100 years from the FCC, right? And so this is kind of like a, look, the air actually is free for everyone, but it's not really free because the FCC regulates who can use this electromagnetic spectrum, and different parts of the electromagnetic spectrum are more valuable to for communications than other parts, right? So if you go to higher frequencies, then you can get more real estate in terms of more spectrum, but your signal cannot go that far, right? So if you pick like a 60 gigahertz spectrum, your signal at a pretty high power level can only say go 2 to 3 meters, and you can't use that more than 2 meters, say from a cell phone battery like that, right? It's going to drain the battery. So therefore, a lot of the communication settled around, around say 1900 to 2000, 2000 megahertz. And then we have our 2.4 gigahertz is our free band, right? Which you don't have to buy a channel, any sort of channel for that or license for that. So what Shannon came up with was basically saying that, okay, given the bandwidth that you have, say 1 megahertz you have, and the signal to noise ratio of, how much at the receive side, right? Suppose you have a signal to noise ratio. What is the ratio of, you're transmitting the signal, but then you have a very noisy channel, right? So say like a copper wire would have a lot more, a lot lower signal to noise ratio than an optic fiber cable. And a wireless channel would have a lot more noise, introduced and a lot lower signal to noise ratio than say a copper wire. And so different mediums over here have, different signal to noise ratios. And that's, you can think of that as, you want a higher signal to noise ratio, the better the communication you will have, the higher the data rate you can have. So what Shannon came up with was basically looking at what is the relationship between, the channel capacity, that is how many information bits can you send across given the channel bandwidth, what is the spectrum that you have, and the medium's signal to noise ratio over here, right? So and he came up with this really very simple sort of theorem called it's basically the Shannon's capacity theorem over here. And that's just saying that, look, higher the signal to noise ratio you have, the more information bits you can get across for the same bandwidth. Or if you have a fixed signal to noise ratio, the more you increase the bandwidth, proportionally more will your information bits, your channel capacity go up. So what does this mean, right? Suppose I want to go from, so when I started working in wireless communication as a junior in my undergrad, that time the Wi-Fi only had 1 megabit per second, and then they had 2 megabits per second, and that was the maximum rate. And then by 2002, Wi-Fi went to 11 megabits per second. There was 802.11 B was the standard after that point, and that was 11 megabits per second. By 2004, they came up with 802.11G and 802.11 A, and so these are all 802.11 is just an IEEE standard for communication. And then the bandwidth went up to 54 megabits per second. Then come 2008, 2010, the Wi-Fi channel band, the new proposals were coming for 100 megabits per second with Wi-Fi. And then, for example, when I worked at Intel Labs, when I was just doing my master's, that time we worked on a different kind of wireless communication approach that was not Wi-Fi based. That was actually using this approach called ultra wideband communications. And there we could send 500 megabits per second. That's because the way the channel was absorbing that signal over there was very different, because we are sending a different type of signal across. So for the same, it was using a lot more bandwidth, right? So for Wi-Fi, essentially you have, say, like a 2.4 gigahertz spectrum, and that just says, okay, well, you have about 70, I think it's about 76 or 75 megahertz of spectrum, and you can decide how to use that. You can use the entire spectrum to send, your message across, or you can break the spectrum into, different channels, so multiple users can use it at the same time. But you can send at a lower data rate, right? So you can use all 75 megahertz, or you can break 75 megahertz into, say, 3 different non-overlapping channels, and send at, less than 1/3 of the maximum data rate if you use the entire channel like that, right? So you have this trade-off now. So you have a very linear trade-off that the more spectrum you have, the larger the channel bandwidth, proportionally more information bits you can get across like that, right? So let me give you another variation, right? So if I have communication and I'm standing near the wire, like, you see the signal bars on your cell phone, right? So what do you think the signal bars are showing you? The signal bars are essentially showing you, this is your signal to noise ratio, but it is just a simplified form of showing you this is a signal to noise ratio. So when the signal to noise ratio is very high, then you get full 4G rate. But when the signal to noise ratio is very low, say, for people who are like lost in the Grand Canyon, then you have very low signal to noise ratio, then you can just send an SMS. All you can do that. You can just send very low data rate, right? So this is just showing you what is the relationship between signal to noise ratio, the channel bandwidth, and the actual information capacity that you can get across, right? And here is just a simple example saying that, okay, well, if I have, so does that make sense so far, at least abstractly? Yes, no, maybe.
Yeah, that makes a lot of sense.
Okay, that is still abstractly, right? So if we look at this kind of example over here, we are we are really thinking about, so we have a source that sends a high pulse. I'll just read it out because even I need a refresher to this example, of 3 volts and a low pulse of -3 volts, right? So we have a 6 volt, signal magnitude that we are sending across. That's a pretty large signal, right? The noise variance of the channel is, is 0.25. And what does this noise variance mean? Is just that you can think of the noise of the channel as a additive white Gaussian noise, or basically it's just a distribution of noise. Generically speaking, is a white noise, which is just saying that it has a Gaussian distribution of the noise, right? So for, say, a center of 2.4 gigahertz, the noise is, the noise energy is uniformly distributed in that sense, right? So for every bit, it is just adding a Gaussian noise on top of that bit as a added signal, right? So the average noise power is equal to its variance. Okay, so, and the bandwidth of the signal. So if we go back to this channel capacity theorem over here, it's saying, we want to get, we want to basically use this to figure out what is the channel capacity. But so what we want to look at is what is the signal to noise ratio, right? So, and that is really basically is modeled as, what is the signal strength squared divided by the variance of the noise. Okay, so so the bandwidth of the channel is 10 megahertz. We're using Manchester encoding. And what is the maximum transmission rate that we can send, right? So how many bits can we actually send effectively across this, right? So now we know, okay, fine, we have Manchester encoding. And so we have our signal strength over here is high, is 3 volts. And so we have this as 3 volts squared. So it's basically the signal divided. So what I haven't showed you here is actually the full formula of getting SNR. So signal divided by 2 squared. And so that's just 3 volts over here, and divided by the noise variance plus 1, right? So don't worry, you don't have to learn this formula. There won't be a quiz question on this formula. It's just to give you some intuition and of this, right? So we basically get, if you just plug into this formula, for the bandwidth that we have is 10 megahertz, that's 10 to the 7. We get 5 times 10 to the 7 pulses per second, but we know we are using Manchester encoding, so we have to divide this by 2. And the signal, so basically the signal strength is basically the signal amplitude squared divided by the noise variance. And so since it's 2 pulses for every bit, the maximum transmission rate that we have is 25 megabits per second, right? So it's 2.5 times 10 to the 7, which is basically 25 megabits per second, is the maximum transmission rate, right? So it's kind of like, Comcast, so say like Verizon, was using, say a copper wire to connect homes using this DSL, right? So digital signal for communication before, and they could say get only about, say 10 megabits per second on that DSL channel effectively to each household. And then they said, look, we can't compete with Verizon, so we have to upgrade our whole infrastructure to use fiber optic cables now. And that's when they started selling Verizon Fios. And with fiber optic cables, they could go well over gigabit per second for a direct connection. And then they said, well, we'll just charge you accordingly. And that's how they can compete, right? Because they just changed the medium. So similarly, Comcast also initially started with copper wires, and then gradually they started replacing copper wires with fiber optic. And so during the mid to late 90s or to early 2000s, just like you see like the Google and Apple booming right now, in those days, the companies that were really booming were all these network companies like Cisco and Juniper Networks, and they were just like generating like billions and hundreds of billions of dollars, and there were a lot of companies that that had maybe like just a few hundred employees, and they were laying out the fiber optic cables across the globe. And I remember reading an article about one of the CEOs of that company. He used to travel out of 365 days a year. He was traveling every day for something like 280 days of the year, because they were just laying the fiber optic cable, from Singapore, say to Bangkok, from Bangkok to the next country, and they were just laying that all out, right? So in the early 2000s, there wasn't that much, fiber optic cable, except for making like a lot of long distance calls or sending like bulk, upload internet communication. But the latencies are very long, and the maximum rate that you could get across was very low. And today we take it for granted because, that kind of bulk delivery of data, first of all, it's commoditized. It's in a strange market. It's commoditized that, you actually have ample capacity now, but we are sending a lot more data. More people are watching Netflix, but at the same time, it's also owned by very few parties, right? And I don't mean like it's owned by AT&T or Verizon. They own sort of the network at the retail level, but the bulk capacity is owned by many other companies that are behind the scenes. And and so a lot of the competition is in how can you build a faster core router to basically now be able to take a packet that is coming from, say, from New York and send that to Singapore versus send that to Stockholm, right? And so so how does it actually decide how to do that without much delay? So what Shannon looked at and came up with was basically a very fundamental principle, saying that given the maximum signal to noise ratio or the distribution of the signal to noise ratio of a particular medium, what is the maximum data, the information that you can send across a channel? And this is not just related to wireless or communication like this is also related to like, much more even abstract communication channels, right? How much information can you get across, whether it is using images, whether it is using videos and so on, right? So how can you encode the data in better ways? Um, so just to give you a last example with this question, I know it's a little bit longer than you asked for, but if we look at like this medium over here has this, channel noise variance of 0.25, right? So just to give you an idea, for a wired line, the the bit error rate, right? So that means how many bits get flipped, out of how many bits that are sent, the bit error rate, or the ratio of how many bits are sent and how many bits are flipped. The bit error rate over there is 10 to the negative 12 on average for say an optic fiber line, and it's about 10 to the negative 7 or 10 to the negative 9 for a wireless communication channel. That means it's almost like more than 1,000 times larger error is there with just switching from optic fiber line to a wireless channel. So, but that will give you an idea that, accordingly, you're going to actually see, a decrease in the maximum information that you can send across a wireless communication channel, right? And that's why we don't have, 10 gigabit wireless communication channels, because the medium itself has a much larger noise variance over there. The medium itself is actually causing the signal to attenuate a lot more, right? So, and we'll cover that when we come to the wireless lectures. But essentially, if I send you a message from where I am and say you are 100 meters away or you're 1,000 meters away, so as the distance goes, the wireless, the receiver basically receives exponentially less energy. You can think of it as the receiver receives 1 over d squared, the amount of energy, or for indoors, it's 1 over d to the power of 4, where d is the distance, right? So it's like a quadratic decrease in the amount of energy from going from A to B over there. So that is also actually causing, that also tells you that if I have line of sight and I have a free, communication, free air communication, I can communicate a much more. But when I have a lot of clutter and furniture and different sort of objects around the house that are causing the signals to have much more reflections and not to just have a straight path from source to destination, then I actually my signal strength actually gets much more degraded because of the environment, because the channel itself is very cluttered. And then other effects like Doppler effect or the relative speed of the different objects that are around you, and they also cause the signal to have a lot of noise in that. So this is just such a fundamental theorem, and he was able to put it in such a simple formula. So don't get fooled by how simple this formula is. But so what is this theorem? Just to give you a last point in terms of history, this theorem basically said that, look, in this case, the theoretical maximum you can send your data is at 25 megabits per second. But the reason you can't really send it at 25 megabits per second is because you have a lot of inefficiencies and impurities in the channel. You have like buffering problems when you receive the packet in the network. And so I'll just give you another example. When I worked at Apple back in 2000, and that time they had just introduced the first gigabit Ethernet port in the Apple desktop, and it was actually in the Apple Mini Cube. And they were like, look, it's supposed to be gigabit per second, but when we actually transmit over TCP IP, we are able to get only 17 megabits per second. Imagine you're promising 1,000 megabits per second and you're only realizing 17 megabits per second. And they were like, Rahul, you find this problem out. And I'm like, okay. And then, so the first thing I did was I went and set up like, in the lab, I put this one machine that was, basically receiving at 1 gigabit per second. But I didn't have other gigabit machines because this was a brand new Apple product that was to be released in the market. And so I connected about 20 other machines that were communicating at 100 megabits per second maximum rate, and they were all basically sending packets to this one machine. So effectively I was getting, say, about 1 gigabit per second of data through a network switch to come to this one machine over here. And I was basically doing like almost like a DOS attack on this machine, right? And I was seeing, well, how much can this machine actually effectively receive? And I had to trace the path of where these bottlenecks were. And these bottlenecks were not at the gigabit Ethernet port, because that had been designed, to actually do that, right? It was doing its job. But when the packets were coming in, they were interrupting the operating system, and the operating system was very sluggish to basically receive the packet, process the packet, and then update that it had received the packet. And so the operating system had a lot of memory, sort of issues, and the operating system was slowing down how much it could actually receive. So then by and by, they say, okay, fine, let's remove bottlenecks from the operating system. Let's remove bottlenecks from how we encode the data. And so over the years, from I would say from the mid 90s to about 2012, 2014, there was this huge effort to say, how do we get to the Shannon's limit for any communications? And they had to come up with very new signal processing techniques to be able to do that. And by about 2010 or so, 2008, there were some really big breakthroughs in coding of these signals, so that they could get within half dB of the channel's capacity limit. And that also marked the end of a lot of research in wireless communication, because you cannot push more bits than Shannon's capacity theorem tells you. And that basically says that, okay, we have figured out how to send, as many bits as we can physically send across a channel, and we can't do any better. And so a lot of the people have to just switch out of working on wireless communications from that point. And that's actually one of the reasons I also just left working on wireless communications and started working on something else. But anyway, this is a little bit less technical and a little bit more history, but we can take some more questions then. So while you're thinking of questions, I'll just flip through the rest of the slides. So we covered this, how to go through serial communication. So there's synchronous, asynchronous, whether you have a clock signal or not. And then how bits are encoded for serial communication. And then how do you actually set up SPI, right? So those are the two sort of things over here. So we have about 25 minutes. We can definitely walk through some of that. What would you like to do? Okay, any questions? I can go over the two examples of, serial communication and SPI communication, if you'd like. Like here's one example on serial communication, and then there is SPI communication, and an example with that. Would you guys like that?
Yeah, I think that would be helpful.
Okay, yeah, I mean, all of this is on the next quiz, so I'm just trying to, but now we are in this flipped classroom, right? We've come up to date with the fashions of teaching well. So, okay, so I was wondering if we could have a lab which used USR for Arduino, or if there were some projects regarding that. So yeah, I mean, so I think that would be nice to have a new lab, but I think the the problem is that we have to build this lab, right? It does not exist. The lab exists for actually working with real hardware. And so what your TAs have been working really, nonstop in the last 3 weeks is making you a new lab that is released today on the RTOS, because you don't have to, because we have to be able to find an RTOS that you can actually run in simulation now, right? So we don't have a way to get you to run hardware. So we can't create these labs, on a day's notice. These labs take like 2-3 weeks to make, while we are all doing our other work also. Uh, so the lab that you would have done would have been communication, not just with the Arduino, but with the embed, and then communication with, better processors, more complex processors after that point. And if you had done the projects in the class, then you would have had a lot more experience with working with these systems. So for now, I know the slides are, they provide some kind of abstract method of instruction. It's not really the ideal way of learning, but we'll go with what we can do right now, right? So um, there's no easy way to actually have, a lab where you have a simulated network and you have serial communication and you actually can observe that. That would have to be constructed from scratch for us to do that. So even our president couldn't predict Corona, how bad it would get. So forget about me predicting that. So let's walk through this example over here, right? So you've covered a lot of different peripherals, and so the communication peripherals with serial communication is no different from that, right? And so essentially, on this Arduino we have serial communications, and this is like really really old school serial communications, and this is kind of the standard communications protocol that is pretty much there in every kind of computer, right? And if it is not there in the new computer, it is emulated, and you're using an emulated version of that communications. Basically, emulation means that instead of the hardware doing this, you actually have software doing a lot of this, because the software is able to run fast enough. So this communications, that what we call serial communications, the full form of that is called USART. It has nothing to do with USA, okay? It just means universal synchronous and asynchronous serial receiver and transmitter. It's a bad name, but it basically puts in all the words that you need to get the message across, right? That it is looking at both synchronous and asynchronous serial communication between a transmitter and a receiver. And so there's a synchronous mode and an asynchronous mode. And so the asynchronous mode is kind of what you may be familiar with, where you have to go to the terminal and set up like, okay, well, this is the baud rate I'm going to send you a message at. This is what I'm going to, this is the start bits. And you're just saying, this is the format that you should be expecting. And now we will just exchange with that format, right? And there is no clock signal required to send message across. As soon as you send me a packet, I know the start of the packet has this format, the end of the packet has this format, and I know what the data bits are, right? So so this USART block diagram here is just the kind of different registers. There is a baud rate register that is just saying what is the clock rate at which I should generate and send my bits across this channel over here. There is a transmit buffer over here that is saying, okay, well, when you want to send a byte, put that byte into this transmit buffer, and I will send that buffer out bit by bit over this transmit line. And there's a receive buffer, and you can see the arrows coming in here, and it's saying, okay, I'm going to receive the message bit by bit, and I'm going to put that into this receive shift register. And then once I get a full receive packet, I'm going to put that into the receive buffer, and you can read that buffer like you're reading, like say the ADC register in the same way, right? So you can think of this almost like a DAC of sending bits across, but bit by bit out of the microcontroller, and receiving bits one by one into the microcontroller here, right? So, and this is a TX line over here and an RX line on the Arduino board. And on the Atmega processor on the top, you can see there's a TX line and an RX line over there, right? So it's just one TX line and one RX line, and we're not using a clock for this kind of, we're just treating it as asynchronous communication, because the computer, we have already instructed the computer by configuring the terminal in the computer to say, okay, like a minicom or hyper terminal to receive a packet of this format. And so we're just saying, look, we both offline have agreed what the format is. Now let's just send messages. And whenever you send me a packet, the packet is kind of self-descriptive, and that can work that way, right? So you're on the Arduino, you're communicating over serial communication over the USB line, right? So basically you have USB physical communication, but you're sending serial packets that are part of the payload. And those serial packets are then sent between these two lines over here. And you can also detect and connect, the Arduino board to an oscilloscope, and you can actually see the activity on the channel over there. Or you can connect it to a logical analyzer and put in the protocol that is being used, and it'll actually show you what is the data, what is the parity bit, and so on the logical analyzer over here, right? So so let's look at like what we are sending and receiving, right? So so if I send an A, for example, A in ASCII is a hex of 6-1, right? So, and when I'm sending that, I'm basically sending, you can see the receiver of the transmitter is sending the signal, and then the receiver is receiving this. It receives a 6, and the 6 is encoded in this manner, and then a 1 is encoded in this manner. And that's basically a 6 is like, it's just just this, right? So 0, 1, 1, 0, and I have that as my 6 over here, and then I have depending on whether it is little Indian, big Indian, accordingly sending that across, right? So, but basically it's just sending a 6, and then a 1 is basically just 0001 over there, and we're sending that across, right? So now what we want to see is how do we actually set this up, when we program this, right? So when you would actually communicate like that, right? So and these are all the features, but let's go to the actual program. First, you want to set up the baud rate. So say the baud rate is basically what is the communication, the transmission rate over here, right? So that's the number of maximum bits that are communicated. Back in the old school days, in like say the late 80s, early 90s, people actually had to use modems to connect to. There was not even the internet at that time, and just to this worldwide, like to the to different kind of networks like Gopher and AOL and different kind of sub private kind of internets, and but they would connect, and they would have to specify what baud rate they need to connect at, and they would have a handshaking protocol, and then they could start communicating over serial communication from the the ISP. It wasn't even called an ISP at that time, to their home, right? So essentially you would have a function that initializes the baud rate. And so baud is like some, for legacy reasons we call the baud rate, it's just saying, well, if I have I have my clock at so for accurate data transmission, the UART model needs to sample the data 16x faster than the baud rate, right? So because we have, it's almost like an ADC, right? We are sampling the data much faster. So we need to figure out, what is this effective baud rate here, right? So if I'm going to be transmitting at 9600 baud, then my baud rate is going to be my my clock divided by 16 divided by this baud rate, and I get 103. Okay, so what is this actually over here is basically just saying, what is this frequency that I need to operate at to be able to transmit at this, right? So all we are doing is just dividing our clock over there, which is 16 megahertz, by 16, so I get 1 megahertz, and then I'm dividing that clock by 9600 and I get 103 over there, right? So because this is almost 1000 and I'm dividing, 1 megahertz by 1000, I should get about 100 over there. So I want to say, okay, enable TX and RX. So these are just some UCSR 0B and UCSR. These are just the UART, control status registers B and C. And they're just saying, okay, let's enable communication. Let's just say, okay, now what kind of format do we have for communication? We can look at that in these registers over here, right? So, but for now, let's just get a high level. First, we set up the baud rate. And let's say there's some configuration over here to say, well, I'm sending you a packet and the packet needs to have a certain format, right? So if I just rewind a little bit, we have this packet format like over here, right? So if I'm sending some ASCII bit value for P, right? So that's ASCII value is 50 for P. And so essentially I have a start bit. And so I need to say, okay, my line is high. When I start to send you some communication, I make the line low. And then I send you the data. And the data is basically going to send 5 and then 0, right? So first I'm going to send you the most significant bit is at the right side. So I'm sending a 5 and then a 0. And then I have a stop bit, which is again high over there, right? So this is just a format. It's saying, look, when I send you a packet, I'm going to send you a start bit. I'm going to send you the data, and I'm going to send you a stop bit. I could also send you parity bits. I could send you some other things, but the actual information bytes are sandwiched between the start bit and the stop bit. So when we go back to configuring, I can say, well, I'm going to send you a start bit. I'm going to send you, no parity over here. I'm going to send you 8 bits per frame, like that, right? And it's asynchronous communication. Then after that, we go and see, okay, how do we now set up the detailed example of setting up the USART. So we have our crystal that's running at this clock speed. And let's say this is some, in our case, we are usually running at say 16 megahertz, but this is running at a different clock speed over here. And one sec, people are just joining and leaving. So yeah, and then, and I have my baud rate. So I want to basically do my initialization to say, okay, well, what is my baud rate that I want to initialize to? And then what is the format that I want to do? We'll come back to the details of this, but this is, I don't want to get lost in configuring the USART only for that, right? So, and so we are basically just writing to this, this register, this configuration register, the UART configuration and status register, control status register over here. And this has all these sort of different things of saying, well, we want to have a receiver enabled, transmitter enabled, the usual stuff to get the communication started. Then we want to basically say, well, do we have parity, odd or even parity, or we have no parity bits? And that's something we covered in the previous lecture about parity bits. Do we have stop bits? Do we have 1 stop bit or 2 stop bits? So again, that's just in terms of the configuration, right? The baud rate register is just saying, what is the rate you're sending at? It has a little bit of a complication because, baud rate doesn't mean data rate, because 1-to-1, because we are really setting in this baud rate register a rate at which the processor is going to be sampling, right? And here we have this 12-bit register that is saying, well, you need to sample 16 times faster than whatever rate I tell you. And this is the value that you need to write to this baud rate register. So then we can configure the status registers over here, right? So if I want to select the number of bits in a frame. So in each frame, I can have anywhere between 5 to 9 bits. A frame is not like, it has to always be 8 bits like that, right? So typically it's 8 bits, but sometimes you might have more stop bits. And so they are taking up more, they're taking up an extra bit or 2. And therefore you have less data that you're going to send across, right? So if I have no parity and I just have 1 stop bit, then I can send 8 bits of data. If I have parity, then I can have 7 bits of data. If I have parity and I have 2 stop bits, then I can only have 6 bits of data and so on like that, right? So parity is just XORing this value. So I can have odd parity or even parity based on this formula over here. It's basically saying how many zeros do I have or how many ones do I have. I'm just calculating that over there, right? So, so the parity is calculated. and we put that parity bit actually in the packet that I send you. And when you receive it, you calculate the parity again for the data bits. And if you have a different parity from what I sent you, then you say, hey, there's one bit flipped over here, right? Or at least an even number of odd number of bits have been flipped in this data. So you have to dump that packet, and you need to send me a message and say, resend that packet again, right? But the resending the message, the resend request, that is of a higher protocol. That's not part of this protocol yet, right? So this protocol is just saying, how do I put the bits into a package, and that package is called like a datagram, and how do I send that across? So when you receive it, you know what is the start of that, what is the end of that, and then you just call send byte, right? And send byte is basically now just going to poll this register and saying, okay, well, if this register is still sending the previous byte and it is busy and it hasn't completed, then don't send the byte. Once this register is saying I'm clear, then send the byte, right? So now the details are in the code, but I'm just telling you the logic. What is it actually doing? It's just saying that I can only send one byte at a time. If the previous request to send the byte has not cleared yet, then I can't send this byte yet. So I have to wait for the previous request to clear, and then I can send that, right? So, and we can look at this code in more detail if you want to. Then, so this is essentially just looking at, well, what is this control status register A? It's just saying, look, transmit has been completed, right? And bit 6 over here is just saying that, transmit complete. And basically it's just this flag bit is set by the peripheral when this transmission is complete. So all we are doing over here is just saying that, is that bit over here set? When do I get, is transmit complete? If transmit is complete, then basically copy the character that I'm sending across into this datagram register over here and send the next character across. And character is basically just the datagrams message, right, that we are sending across. So it's almost like this is kind of like a mutex that is saying, well, only once the flag is set that I'm clear to send again, then I can send the next byte. I can't like overwrite the current byte that is currently in transmission and dump on that register over there with my new character. Then that will garble all the stuff. So just kind of just keeping a mutex on the transmit register over there. How do you receive? Here is just saying if the if the reception is I receive only when it's ready to receive, right? So if it's busy and it's still it's not ready to receive, it's busy with the previous receiving the previous byte, then I'm not going to try to receive the next packet. And so I'm just going to say when the receiver is ready to receive and it is not busy, then, and how do you look at that? Then you look at this US CR0A and 80, right? And then you just see what that means over here is that the receive is complete. That 80 is basically a 1 at this, and it's saying the flag bit is sent when all the unread data on the receive buffer is cleared. That means I took the received, I basically copied over the received data from the buffer into my local receive buffer, and then it basically sets that flag and says, look, the receiver is ready to receive the next packet. And so when I'm ready to receive the next byte, then I can actually then copy the next byte over again. So just again, putting a mutex almost in that sense, right, over here. So if you put it all together, we are initializing this to set this baud rate over here, which, we are dividing by 16 and by this baud rate to get this number of what the baud rate is, because essentially just a more compact way of putting the baud rate. Then how do you send a byte? How do you receive a byte? And then the main is over here, right? We're just initializing the USArt at 9600 baud rate. Normally you would use like 115 kilobaud, like that. It can go up to much higher baud rates. And then you want to say, okay, receive a character, send this. So basically this is the simplest program that you can have on two Arduino nodes or 2 microcontrollers. It's just a count program. That means I send you 1, you add 1 to that, and you send me 2, I send you 3, 4, 5, 6, 7, 8, and we just go ping pong, ping pong. But then we know which packet got dropped because we say, well, I sent you 7, you didn't send me 8. So that means 8 got dropped. And then I basically didn't receive anything. So then we just stopped communicating because I didn't receive something and you didn't, and I don't have anything to send you yet. So that's an easy way to test a channel, right? So same way over here, how do you put it all together? Then this walks you through that same example in much more detail now, and on how to configure this register, and then how to start sending that, right? So that's just an example of of being able to communicate over serial communication, and how we communicate over SPI is a little bit more complex because with SPI, but it's not too different. With serial communication, it's just pairwise communication. That means just you and me can communicate one party to another party. But for serial peripheral communication, it said, well, one party can actually communicate to multiple parties. And that one party is called the master, and all these other parties are called the slaves, right? I mean, we don't like that way of, talking right now or anytime. It shouldn't be a good way. But here, this is actually slave as in terms of a machine slave. It's not a person slave. So we are not being derogatory to that peripheral in any way. So even in the PC world, it's perfectly fine to call this, what a master, slave, leader, follower. It's not necessarily a leader follower, right? And there's no one following here. But the master is essentially, you can think of that as your USB hub. And then the slaves are like, like I have this USB hard drive over here, or I have some other USB peripherals, then they are all the USB slaves over there, right? So a single master can, and then so essentially the single master can send a packet to an individual slave over here, and an individual slave can basically send to the master. So the master has a master out, slave in, and that's basically a line out to everybody else. And then the master has another line called a master in, slave out. And that's flipped on the slave side. So on the slave side, it receives on the master out, slave in, and it sends on the master in, slave out line. And then you have this slave select lines over here. And basically the slave select line is just a way, like in Zoom, you would be able to like raise your hand, right? And it's just saying, hey, I'm slave 2 and I'm raising my hand and I want to send a message to the master. So slave 2, and you can see that this is active low, right? Slave 2 will just basically raise their hand by pulling that line low and letting the master know that I want to send this message next. And then the master says, okay, you can send that message next. And this is also a synchronous protocol, right? It also has a SPI clock over here. And so you can actually send, like, say, up to like 400 megabits per second, pretty high speed data. And this is one of the simplest ways of communicating between multiple chips. So say you got a new ADC chip, or you got an IMU chip, or you have a wireless transceiver. All of them will communicate to the microcontroller using SPI. So you want to know how to set up SPI right over there. Or you have essentially your LCD screen that is communicating to the microcontroller. You would have that, right? In this example, we have a radio over here that is communicating over SPI, and we are being able to say, okay, I received a packet, and the microcontroller can get that packet over SPI. Or if it wants to send a packet, it can send the packet over SPI to the radio, and then the radio will send that over the antenna like that, right? So you use SPI in this touch pong lab. You are actually coding SPI when you are configuring the controls of this the LCD screen by running that sequence of control signals to configure the LCD screen. SPI is used in optical mouse sensors, for example, and then there are many different things, right? And then at the end of this lecture, we basically have an example of how to set up the master and the slave, but it is essentially very much the same thing, right? It is saying, okay, now you set up the master to receive and transmit, and then the slave to receive and transmit. And so you're going to write separate programs for the transmitter and the receiver. And if you'd like to, we can go into this example in more detail. I didn't get a specific question to go through this example in more detail, but if you want to, we can do this in the next lecture, since we are about out of time today. But it would help if you actually just read this code and say, okay, I'm confused at this point. Why do you have this while loop? And I'm confused there. Or why do you have this while loop over here? How does this communication get initialized for the first time? And how do different slaves, raise their hand so we can have different, what if multiple slaves want to communicate at the same time, right? So those are questions that I would expect from you guys to have. But essentially, this is all so far fair game for the quiz, but you can read through this example. And there is an actual example of, a more interesting example of a mouse sensor, of how do you initialize that and basically set up SPI or serial SPI to communicate with the microcontroller. And basically the mouse sensor is essentially just a camera sensor, like an optical flow camera sensor. And we are using that, right? So, and when we had projects in the class, pretty much every team was, running SPI to work with some Nintendo Wii kind of sensors for infrared communication or infrared sensing and so on. So, but I'll pause over here. I mean, there's a lot more we can talk about, but it depends on your questions at this point. And so let me know if you have any other questions or, I mean, I think it's one thing to live your life quiz to quiz. The other thing is to learn something through this, right? So I know we are also adapting our course, so I think we are doing a pretty good job in adapting your labs really well and the quizzes. So because you don't have much real world experience working with actual hardware for this course, but then the lab that is coming out today on programming in the free real-time operating system simulator, that will make you do like part one is on concurrency program. So basically actually coding up the concurrency problems that you have done so far, looked at in the lectures and in the quizzes. And part two is essentially, running multiple task sets and seeing which ones, have a deadline failure or a deadline or can meet their deadlines, which are schedulable and not. And if you run like 20 of these iterations, then you can basically come up with your own graph of seeing, what is the kind of utilization bound that you capture with an actual like task set in a real-time operating system using rate monotonic scheduling to that. So, okay, so I'll stop here. Any other questions?
Do we need to know the difference between SPI and I²C?
No, we didn't cover I²C, so
Okay.
we didn't ask you anything on I²C.
Okay.
But good question, yeah. Yeah, so I²C is another communications. There are many of these, right? So there is a CAN bus, that's what's used in cars and washing machines and different kind of robotic systems. So yeah, but yeah, normally you would cover a lot of that in a project like that, but you get full credit for no project. So lucky so in that way. Okay, any other questions? Okay, all good in that case, then we'll catch up again on Tuesday and we'll have a new set of lectures on, wireless communication for next week. And then your quiz following that will be on all of this communication. And we'll also have a lecture on control systems and how to do PID control, because you would have had a balancing bot lab, but we do not have that, but it's still good to know the basics of PID control, and we'll cover that also in the later lecture. So you will have basically one last lab going out today. It has two parts. Part A is due next Wednesday. I think that is on the 21st, and part 2 is due on 28th. It's a pretty light lab, and that's the best we could have with having like basically a microcontroller RTOS simulator, and where you can actually at least push your learning to that extent. So there's not much compromise in terms of the core material of the course. The only compromise is that, you don't work on an actual project in this course, but I think a good 1/3 of the class was, we had made that optional anyway this semester, but from next semester it won't be optional, but I won't teach next semester. I won't be teaching this class next semester. So you guys had the yeah. So also, like, you in a few weeks you'll get some course evaluation thing, and obviously evaluate how we've adapted to the changing situation in the course. And that way I think you guys are like super lucky. You have a really awesome set of TAs, and not enough people are showing up on office hours, but I'll leave that to you guys to show up on office hours. But the TAs are always there, right? Everybody has at least 2 office hours a week, and we have recitations, and it's usually the same gang that shows up for this lecture, which is less than 1/3 of the class, but that's fine. Okay, if there are no more questions, we'll stop here, and and then we can continue next Thursday. On Thursday.